Here we have 5.1 of the exercise from the textbook, and this is looking at electric current. So for question 1, when a current is flowing through a wire attached to a dry cell, we've got to choose the correct answer. Well, let's just discuss what actually happens here. So if I've got a dry cell here, sorry, excuse the diagram here. So there's maybe as a resistor there, and you've got a current. This is a dry cell. Now the short one is the negative and the long one is the positive. That's how we draw it. The electrons are actually the things that move in the wire, so they actually go from the electrons actually move from the negative through to the positive. They're repelled by the negative and they're attracted by the positive. So an electron will come in over here, and you'll get this flow of electrons going through, flow of current. Now, in actual fact, we denote current with a big I, and we usually take it as going from positive to negative. Traditionally, it's always been like that. But the things that actually travel in a wire, say a copper wire, are the electrons. So it would be negative charges from the negative to the positive. So it would be C. Question 2. The total charge passing the same point in a conductor during 2, and this over here is a microsecond, of electric current of 7.5 milliamps. Okay, so in looking at this, let's call up our data booklet. We're actually going to be using this formula over here. We're going to be using that formula over there, and so let's just write that in over here. So I is equal to Q over T. I'll leave that out there. Actually, I'm going to probably close this now. So we're going to use that formula Q, this one over here. Now we want to work out the charge, so Q is equal to I times T from this formula over here. We have got our current is 7.5 times 10 to the negative 3 amps, and the time is 2 microseconds, so it's going to be 2 times 10 to the negative 6 seconds. So we're going to get 15 times 10 to the negative 9 coulombs. So this one over here would be your nanocoulombs, your NC there. So it would be equal to 15 nanocoulombs. So it's really quite important that you know what these terms are. You can actually find them in your data booklet. If I go to my data booklet and I go back here, I think we can find them here. Here they are here. So there's your nano, and so they are all given there if you don't remember them. Going back to our formulas here. Alright. Going on to question 3. It says an electrical heater raises the temperature of a measured quantity of water 6 times 10 to the 3 joules of energy is absorbed by the water in 30 seconds. What is the minimum power rating of the heater? Now, the power rating is given in watts, and we know a watt is a joule per second. So if I've got here 6 times 10 to the 3 joules, and it's 30 seconds, I'm going to have to divide that by 30 to get my value. So that's going to be basically 6,000 divided by 30. One of those will cancel, so we're going to be left with 200. So it would be B over here, 2 times 10 to the 2 watts. Okay, because here you're going to have your joule and your second, so you're going to get your joule per second, which is a watt. Question 4. If the power developed in an electric circuit is doubled, the energy used in 1 in 1 second is halved, doubled. Well, we can see that our power is equal to our work over our time. So work is equal to power times time. So if the power is doubled, then obviously our work is also going to be doubled. There's a directly proportional relationship here. So that would be B. The electron volt is defined as, well, it's actually defined as A, the energy acquired by an electron which passes through a potential difference of 1 volt. We get this from our formula here, this formula over here, this one here, where VE is equal to the energy. The definition for a volt or potential difference is work done per unit charge. So work is equal to V times Q. So when I pass an electron through a potential difference of 1 volt, the work done on it is 1 volt times the charge on an electron, and we say that as an E. So we get 1 eV. Now 1 eV corresponds to 1.6 times 10 to the negative 19 joules, because the charge, this charge here, the charge of an electron is 1.6 times 10 to the minus 19 coulombs. So I've got to times the 1 by this charge to get me my value in joules. We often just leave it as an EV. Alright, actually let me just close this off. Fine, so there we have, that's question 5, going over the page. We're going to question 6. The definition of the unit of current, the ampere, is based on, now it's actually based on this over here, the force per unit length on a parallel current carrying wires. When you have 2 wires, there is a force, and if they both got a current in them, if they both have a current in them, they will exert a force on each other, and that force, the amount of that force is dependent on the current, and that is where the definition of the ampere comes from. You will get that definition, I'll get that definition to you later, but it's dependent on that. 7. Identify the charge carriers in a length of copper wire. Those would be electrons. An aqueous solution of sodium chloride, that would be your sodium ions and your chloride ions. And the atmosphere during a lightning storm, those would just be charged particles. It could be dust particles, all sorts of things. Could be water droplets, many different things can have the charge on them, so those would be charged particles. The speed with which electrons move through a copper wire is typically 10 to the minus 4 meters per second. Explain why it is that the electrons cannot travel faster in a conductor. Basically what happens is that they interact with the electrons as they are moving through, so there is resistance. And explain why the electron drift produces heat. Well, as they move through, they bump into those other electrons and other particles, and that causes those particles to gain energy. There is energy transfer, and they speed up, and therefore they get there is heat.